In the 21st century, the surge in data became both a blessing and a challenge. Enter data science, where techniques like machine learning and artificial intelligence help unlock the secrets hidden within space data. Scientists discover patterns, gain insights, and navigate the maze of information. We hear an awful lot about how data is the oil of a new generation, the lifeblood of countless industries that will use what we generate through our phones, planes, and automobiles to their benefit. Data is no longer just numbers and statistics. It is a powerful tool that can uncover patterns, predict future outcomes, and optimize performance. Companies like Google, Amazon, and Facebook have built entire business models around collecting, analyzing, and monetizing data, demonstrating the immense value it holds in the modern marketplace. Data is the backbone of today's digital economy, driving decisions, shaping strategies, and transforming industries. From small businesses to multinational corporations, governments, and individuals, data has become an invaluable asset that fuels innovation, efficiency, and competitiveness.
The world produces 2.5 quintillion bytes of data daily, but that figure should grow at an accelerating rate as more people and devices are connected to the internet. Unlike tangible assets, data is a quasi-infinite, non-linear growing asset. While this data explosion has created many challenges such as consolidation of data, cybersecurity, and democratization of data, these are heavily outweighed by the significant opportunities offered by these amazing new data assets.
So, bear in mind how much data is being generated by an agency whose remit not only covers everything here on Earth, but everything we can see in the known universe. That's the job of NASA, one of the biggest generators of data gatherers and distributors in the world on everything from the latest climate data to, as we saw quite recently, the hidden secrets of our solar system's ringed planet, Saturn. Data collection is a methodical practice aimed at acquiring meaningful information to build a consistent and complete data set for a specific purpose.
Data collection revolves around gathering raw data from various sources,
with the objective of using it for analysis and decision-making. It includes manual data entries, online surveys, extracting information from documents and databases, capturing signals from sensors, and more. In machine learning projects, data collection precedes such stages as data cleaning and pre-processing, model training and testing, and making decisions based on a model's output. Note that in many cases, the process of gathering information never ends, since you always need fresh data to retrain and improve existing ML models, gain consumer insights, analyze current market trends, and so on. In machine learning projects, a significant portion of the overall effort is dedicated to data collection and preparation. While the exact percentage varies depending on the project, it's common for data scientists to spend 80% or more of their time on data-related tasks. NASA collects data using a variety of platforms, instruments, and techniques, both on Earth and in space. They utilize satellites, aircraft, balloons, and space probes to gather data on Earth and beyond, transmitting information back to Earth using radio waves or lasers. The Opportunity rover worked on Mars from January 2004 through June 2018, when a monster dust storm silenced the golf cart-sized robot for good. Originally intended to last 90 days, the machine crawled more than the distance of a marathon during its long and accomplished life. At the time of its death, the rover's odometer read 28.06 miles. One of Opportunity's greatest scientific findings was confirming the presence of standing water on Mars for long periods. Mars may help us to learn more about the mysteries of the solar system. Its similarities to Earth, such as the presence of water ice, seasonal weather patterns, and geological features like volcanoes and canyons, make it a prime candidate for understanding planetary evolution and habitability. The quest to discover microbial life, past or present on Mars, could revolutionize our understanding of life's existence beyond Earth. Research on Mars also enhances our technological capabilities, driving innovations in space exploration, robotics, and remote sensing. Scientists are dedicating significant time and resources to unravel the secrets of Mars, driven by the quest for knowledge and the potential benefits for humanity's future.
The search for extraterrestrial life is one of the most fascinating and complex challenges in modern astrobiology. Biosignature detection, the identification of signs of life in samples or data, is a crucial aspect of this search. Recent advancements in technology and methodology have significantly improved our ability to detect biosignatures, paving the way for future breakthroughs.
Future missions to icy ocean worlds, such as Europa and Enceladus, will evaluate the habitability of and search for potential biosignatures from these worlds. These missions will benefit substantially from autonomous science methods to process high volumes of collected data and to prioritize detections of signals of interest for the first available downlink. The exponential rise in space data captured from satellites, telescopes, and interplanetary probes requires AI's analytical capabilities. Modern space instruments generate terabytes of data daily, far more than scientists can examine manually.
A global team of astronomers and machine learning researchers today announced the release of the Multimodal Universe, a groundbreaking 100 terabyte dataset that brings together hundreds of millions of astronomical observations in unprecedented detail and scale. This massive collection of space data aims to revolutionize how artificial intelligence can be applied to unlock the mysteries of the cosmos.
All this data is originally stored in various places, such as SQL databases, NoSQL databases, text files, and various cloud storage.
A dataset
Is a collection of data that can be used for analytics or to train machine learning models.
A dataset is like a collection of data,
Primarily used for analysis, while a database is a system designed for storing and managing data efficiently. The major difference lies in their application. Datasets are typically employed for analysis purposes and databases for ongoing data management tasks.
DataNASA.gov
Is NASA's clearinghouse site for open data provided to the public. Tens of thousands of datasets are available for you. The majority of dataset pages on data.nasa.gov only hold metadata for each dataset. It is common for the actual data to be held on other NASA archive sites.
The size of a dataset plays a critical role in machine learning model performance because it directly impacts a model's ability to generalize to unseen data. A larger dataset typically provides more examples of the underlying patterns the model needs to learn, reducing the risk of overfitting, memorizing noise or specific examples, and improving the model's ability to handle real-world variability. For instance, a small dataset might not capture enough edge cases or diverse scenarios, leading to poor performance when the model encounters new inputs. Conversely, a sufficiently large dataset helps the model recognize broader trends, making predictions more robust across different scenarios. The rule of thumb rule is that you need at least 10 times as many data points as there are features in your dataset. For example, if your dataset has 10 columns or features, you should have at least 100 rows. The rule of thumb approach ensures that enough high-quality input exists.
The appropriate size of an ML dataset depends on several factors, including the type of problem, the complexity of the model, and the desired accuracy. While large datasets generally lead to better model performance, the more is better principle has limitations.
Data splitting in machine learning is the process of dividing a dataset into distinct subsets for training, validation, and testing of models. This is crucial for building accurate and reliable machine learning models. Training. The majority of the dataset is fed into the model so it can learn to identify and analyze patterns. Validation. The validation set is used to test the model over the course of its development. It allows the model's programmers to assess how it performs relative to other models and hyperparameter options, while also helping to identify potential problems. Testing. The test set is the final piece of data, intended to assess the finished model's accuracy. It simulates the real world in an effort to provide as unbiased a picture of the model's performance as possible. It's generally accepted that the optimal ratio of training to testing and validation is roughly 70 to 15 to 15. Another common split is 70 to 20 to 10.